Jai Hind everyone. Myself Dr. Vanna Sharma from Ajay Kumar Garg Engineering College, Ghaziabad. The subject which I am teaching is engineering physics, and its code is KAS 101T in odd semester, and in even semester code of this subject is KAS 201T. The topic which today I have taken for discussion, that topic belongs to electromagnetic field theory, which is unit 2 in engineering physics. Under this electromagnetic field theory, the topic which today I am going to discuss, that topic is displacement current, and some subtopics which are related to this concept of displacement current. Now, the first question arises that what is this displacement current, and why there is a need of discussion of this particular term, displacement current. So, in order to understand, I am going to give you a brief idea about this electromagnetics or electromagnetic field theory. As you all know that electrostatic, this particular branch of physics that deals with static charges or electric field. And when I'm saying magnetostatics, then that particular branch is dealing with moving charges or magnetic field. So, two different branches, two different fields are there. One is electrostatics, which is dealing with static charges or electric field. And the other one is magnetostatics, which is dealing with moving charges. The combination of these two means the combination of electrostatics and magnetostatics. That is a new branch which is known as electromagnetics. And this electromagnetics that deals with both type of charges which are at rest as well as charges which are moving. So this particular branch, electromagnetics, that is the beautiful correlation between the charges which are at rest, or in other words, I can say it is a correlation between electric field and magnetic field. This particular branch that relates electric field with magnetic field. So, as we all know that each and every branch of physics, or whatever I will say, that depends upon certain laws or certain principles. Means, if I'm saying electrostatics, it is based upon certain laws, certain principles. Like, if I will quote one or two, then it is Gauss law in electrostatics, Gauss law in magnetostatics, Faraday's law of electromagnetic induction, and other principles, which are the base of electrostatics and magnetostatics. So, since this electromagnetics or electromagnetic field theory, it is a combination of both the branches, that is electrostatics and magnetostatics. This particular branch is also associated with four basic equations. So, what I am trying to say here, that this electromagnetics or electromagnetic field theory, that depends upon four principles, four equations actually. And these equations are nothing new. Basically, this concept was a concept of Maxwell equations, which are actually the base of electromagnetic field theory. This concept was first time conceived by James Clerk Maxwell, and the name for those four equations is Maxwell equations. So, the heart, the base of this electromagnetic field theory, this electromagnetics, is a set of four equations. And these four equations are actually based upon four laws of electrostatics and magnetostatics. So, actually these equations are the differential form of four different laws of electrostatics and magnetostatics. So, I am mentioning those four laws here just for the sake of information. The first equation, first Maxwell equation is actually is actually the differential form of Gauss law in electrostatics. Just give me a second. First equation, that is obtained from Gauss law in electrostatics. Second equation, that is the differential form of Gauss law in magnetostatics. Third one, that is the differential form of AMPHER'S law. And the fourth one, that is differential form of AMPHER'S law, but in modified form. So basically you have four equations, and those four equations are the differential form of four different laws of electrostatics and magnetostatics. and the entire electromagnetics, that how the electromagnetic radiations are propagating in a certain medium. If you want to describe the energy associated with the electromagnetic radiation, if you want to describe the radiation pressure or momentum, in order to describe each and every parameter, we require these four Maxwell equations. These equations will give you the complete information in electromagnetics. And in these four equations, the fourth equation, which is actually correlating electric field and magnetic field, that equation is a differential form of modified Ampere's law. And in that modified Ampere's law, we have two terms which are giving us magnetic field. We have two type of currents which are giving us magnetic field. The first one is ordinary current, and the other ordinary current, or you can say conduction current. And the second type of current, that is also a current, but that current is not just like ordinary conduction current. Its properties are different. It is a different type of current, and the name is displacement current. So the topic of our today's discussion in electromagnetic field theory is actually displacement current. So now we will try to understand that why we have this term displacement current, and on the basis of that concept of displacement current, we will try to understand that there is a need of modification in our Ampere's law. So we will see that what is that modified Ampere's law on the basis of this concept of displacement current, and finally we will write an expression for displacement current density on the similar lines of conduction current density. So this is our topic of today's discussion. Now with the help of this simple diagram, we can understand the entire concept of displacement current. So let's try to understand what is our displacement current actually. So in order to understand this displacement current, we have a parallel plate capacitor here. You have this parallel plate capacitor. So this is the diagrammatical representation of one part of that parallel plate capacitor, one plate, and this is the another plate of that parallel plate capacitor. So in this parallel plate capacitor, if you will connect this capacitor with a battery of a particular EMF or voltage, then current will flow in the circuit, current will be there in this circuit, and when you will connect this parallel plate capacitor with the help of a battery, then there will be charging of these two plates. And during that process of charging, and if you will open the key, there will be discharging of those two plates. So basically, during the process of charging and during the process of discharging, we have two type of currents in this particular circuit. The first type of current, which is our ordinary conduction current, that will be there in these connecting wires. So you have those connecting wires, and in those connecting wires, when you will apply a potential difference, a voltage, then because of that potential difference, electrons will start drifting, electrons will start moving in a certain direction. And because of the movement of those electrons, you will have that ordinary conduction current, which is due to flow of charge. That is your ordinary current. So you have two type of, as I mentioned, two type of currents will be there. The first one, which is there in connecting wires, and that is because of movement or flow of charge. But there is one more type of current which is there in the circuit, and that current is there in between these two plates. If you will carefully see these two plates, then there is no actual flow of charge between this plate. I am referring this plate as P1 and the second plate as P2. So when you are charging these two plates of parallel plate capacitor, then there is no actual flow of charge between P1 and P2. So if there is no actual flow of charge, then there cannot be ordinary conduction current, which we know is due to flow of charge. Since there is no actual flow of charge between these two, there cannot be conduction current in between these two plates. But there is a current between these two plates of this parallel plate capacitor, and that current is not because of flow of charge. That current is due to a time varying electric field. So what I have mentioned, there is a second type of current which is known as displacement current, and that current is there when there is no actual flow of charge. There is a time varying electric field here. That time varying electric field is there in between these two plates, and because of that time varying electric field, you have that displacement current. Now, why I'm saying that you have a current here because of time varying electric field? You can understand it with the help of Faraday's law of electromagnetic induction. So I'm just trying to correlate that why I'm saying there is current between these two plates. In order to understand that, I'm referring Faraday's law of electromagnetic induction. So you all know, according to Faraday's law of electromagnetic induction, rate of change of magnetic flux is equal to induced EMF. This rate of change of magnetic flux is induced EMF. And when I'm saying change in magnetic flux, so you know magnetic flux, that is basically the combination, or you can say product of magnetic field and the area. So when I'm saying time varying or rate of change of magnetic flux, then in that case, actually the term which is changing, that is magnetic field. So this term is actually representing a time varying magnetic field. And that time varying magnetic field is actually responsible for EMF in the circuit. And when I'm saying EMF, you can easily correlate that EMF with electric field. So what is the meaning of this Faraday's law of electromagnetic induction? Simple meaning is, if you have a time varying magnetic field, why I'm saying magnetic field? Because magnetic flux is related to magnetic field. So this time varying magnetic field, that is giving you an EMF, or you can say electric field. So on the similar line, I can say, if we have a time varying electric field, then there will be a magnetic field. If you have a time varying magnetic field, you have electric field. On the similar lines, if you have a time varying electric field, then there will be magnetic field, right? So because of a time varying electric field between these two plates of parallel plate capacitor, you have magnetic field there. And whenever we have magnetic field in a circuit, we can say there is current. But that current is not due to actual flow of charge. That current is because of a time varying electric field. So why I'm saying there is current here, that current is because of a time varying electric field here, and that time varying electric field is actually giving us magnetic field. And whenever we have magnetic field, we can correlate it with current. So we can say in the connecting wires, you have ordinary conduction current, and between these two plates where there is no actual flow of charge, we have displacement current. And I hope up to now you have this point is very much clear to you, that this current which is there in between two plates, that current is not due to actual flow of charge, that is because of time varying electric field. So I will explain it in detail when I will explain the charging and discharging of these two plates in the subsequent slides. But up to now, you should understand that between these two plates where there is no actual flow of charge, we have a time varying electric field which is actually giving us a magnetic field, and we are correlating that magnetic field with the current, and that current is displacement current, right? Now here we have some, I have mentioned some characteristics of displacement current in these slides. So basically displacement current is the current which is there because of time varying electric field. So that is the basic idea. This time varying electric field, that is giving you a magnetic field. Displacement current has the units of electric current. It has properties similar to current, means this is giving us magnetic field. That is a most important characteristic of current here, that whenever we have current, we have magnetic field. So in this particular case, this time varying electric field is actually giving us a magnetic field. So that is property of displacement current is similar to the properties of conduction current. Just give me a second. Displacement current is another type of current apart from conduction current. So up to now, this particular point is clear. Conduction current, that is because of actual movement of electrons, whereas displacement current is due to time varying electric field. It is a vector quantity, just like our conduction current. Now, on the basis of this concept of displacement current, we will try to understand that why there is a need of modification in Ampere's law. So, from this particular slide and from the subsequent slides, now it will be clear that how you are getting that displacement current. So, in order to understand this, what we have done, we have taken a parallel plate capacitor, and that parallel plate capacitor is actually connected to a battery of EMF E, and two closed loops are taken. So, two closed loops are there. The first loop is taken here, which is in connecting wires, and the second loop is present between the two plates of this parallel plate capacitor. You can understand it like this. You have this parallel plate capacitor, and this parallel plate capacitor is connected to a battery of EMF E, right? So, E is the EMF of this particular battery which we are using in the circuit, and these are the two plates P1 and P2. Now, as you can see here, we have two closed loops, and you can understand these two loops like this. The first loop is present in these connecting wires, and we have taken our second loop between the two plates just to understand the two different type of currents. So, according to Ampere's law, the closed line integral of magnetic field, you all know that closed line integral of magnetic field is actually mu naught times the current enclosed. Means in a closed circuit, the current which is flowing in that closed circuit, that is actually responsible for the magnetic field. So, in this particular Ampere's law, this I, which is mentioned over here, this I is actually our conduction current. So, according to Ampere's law, this closed line integral of magnetic field is mu naught times the current enclosed. Now, what we are going to do? We are going to apply this Ampere's law for both the loops, for loop C1 as well as for loop C2. So, in this circuit, what we have current in these connecting wires because of the flow of charge. So, when you are closing this key K, this is the key which is controlling the circuit. So, when you will close this key K, current will start flowing, and when the current will start flowing in the circuit, we will see that what is the amount of magnetic field for loop C1 for this particular loop, and what is the amount of magnetic field for loop C2. Since this first loop that is present in these connecting wires, and in those connecting wires there is actual flow of charge, so there will be magnetic field. But in the for the second loop, which is there in between these two plates of parallel plate capacitor, since there is no actual flow of charge, so according to Ampere's law, there should not be any current. So now we will try to verify this Ampere's law for both the loops, for both the closed loops, similar type of loops C1 and C2. So actually what happened when this key K is closed, that can be understood from the circuit diagram. So what you have a closed loop here, and another second loop is present in between these two plates. So when key is closed, current will start flowing in the circuit. And when current will start flowing in the circuit, let I is the current flowing in this circuit here. When you will apply Ampere's law for loop C1, so if I will apply this law for loop C1, then according to Ampere's law, this V dot dl is equal to mu naught times the current enclosed. It means Ampere's law, according to Ampere's law, we have magnetic field here, and that magnetic field is because of flow of charge or because of current in those connecting wires. So in the connecting wire where we have that first loop, this loop, I'm referring this loop as C1. So for first loop C1, since you have flow of charge there, you have conduction current there, and because of that conduction current, according to Ampere's law, you have a magnetic field here, which you can easily find with the help of this particular equation, right? So this Ampere's law that holds good for loop C1, which is there in connecting wires. Now we are applying the same Ampere's law for loop C2, but you have to remember what is the actual position of loop C2. That loop C2 is there in between these two plates. This is the this is the first part of that plate, and this is the second part. So actually what is happening, when you are closing the key here, and after closing the key, current will start flowing. And when current will start flowing, the charging of these two plates will start. And when the charging of these two plates will start, actually these plates will take some time to get fully charged. Suppose these two plates, they are taking 10 seconds to get fully charged. So from 0 to 10 means from the point where the charge was 0 over these two plates, and up to the time when the charge over the when these two plates are fully charged, 10 seconds are taken by these two plates. Means to get fully charged, these two plates are taking some time, and during that process of charging, means from 0 to 10 seconds, at different times, the charge over the two plates will be different, because 10 seconds is the time taken by the two plates to get fully charged. Means from 0 to 10, at different times, the charge over the two plates is different. And once these plates will get fully charged, suppose you have opened this key, and if you will open the key, then the discharging of the two plates will start. And again, these plates will take some times to get fully discharged. Means for the charging, these plates are taking some time. To get fully discharged, again plates are taking some time. So during the process of charging, at different times, charge is different. And during the process of discharging, at different times, the charge over the plates, over the two plates is different. So actually, what is that factor which is changing for these two plates with time? So you can easily see here that during the process of charging and during the process of discharging, the charge over the two plates is different. So what you have to do now, you have to apply the same Ampere's law for this loop C2 here. So if you will apply this Ampere's law for loop C2, then you can see here no actual flow of charge. Since no flow of charge is there, no conduction current is there, according to Ampere's law, this B dot dl for loop C2 is mu naught times 0. No flow of charge, no conduction current. So if mu naught times 0 is there, it means according to Ampere's law, there cannot be any magnetic field in this loop C2. For loop C1, you have magnetic field, and the reason of that magnetic field is also clear. Reason of magnetic field is actual flow of charge, or that current which is there in those connecting wires. That is the reason of the magnetic field for loop C2. But for loop for loop C1, but for loop C2, since no actual flow of charge is there, so the field for loop C2, that should be 0. No magnetic field according to Ampere's law for loop C2. But irony is, if you will place a magnetometer box here between these two plates for this loop C2, if you will place a magnetometer box here, if you will place a compass here, then that will show a deflection. As you can see here, you have a deflection in the magnetometer box which is placed between these two plates of parallel plate capacitor. And that deflection in the magnetometer box, this deflection, it is indicating that we have magnetic field even for loop C2. But according to Ampere's law, there cannot be magnetic field. But actually, practically, there is a magnetic field between these two plates of parallel plate capacitor for loop C2, where we do not have any movement of electrons, any flow of charge. So what is that reason? What is that factor which is responsible for this magnetic field, which is responsible for deflection in this magnetometer box. We have to understand that what is the basic idea, what is the basic reason of magnetic field for loop C2. And the reason is very much in front of you. As I have mentioned, during the process of charging at different times, the charge over these two plates is different. And you all know, for a parallel plate capacitor, electric field that is basically given by this Q upon A epsilon naught. Now at different times, means if I'm saying T1 and T2, I have taken those two times. At T1, during the process of charging, let Q is the charge over these two plates. At time T2, since T1 and T2 are different, so the charge, those charges over the two plates are also different at different times. Means because of different charges over the two plates at different times, we have a time varying electric field there. So the factor, which is actually the variable factor here, that is the time varying electric field. What you have here? You have actually a time varying electric field. Means you have an electric field here which is actually changing with time. So during the process of charging, you have a time varying electric field. And again, during the process of discharging, again you have a time varying electric field. So that time varying electric field is actually giving this deflection in magnetometer box. So this deflection, which you can see here, that deflection is because of time varying magnetic field, time varying electric field. So this time varying electric field is giving you a magnetic field. So this time varying electric field is giving us a magnetic field. So I hope now it is clear that in C1, the magnetic field is because of flow of charge. Whereas for loop C2, we have magnetic field because of a time varying electric field. Means two different factors are there which is giving us magnetic field. For loop C1, flow of charge, that is giving us current, that is giving us magnetic field. But for loop C2, a time varying electric field is giving us a magnetic field. It means from this entire discussion, it is clear that this AMPHER'S law that needs some correction, that needs some modification, because it can explain the presence of magnetic field for loop C2 in connecting wires, but it is not able to explain the presence of magnetic field for loop C2. So basically this AMPHER'S law that was modified, and in the modified form, this closed line integral of magnetic field. Basically, this closed line integral of magnetic field is mu naught times the total current enclosed. So when I'm saying total current enclosed, then two different type of currents are there. The first one, which you can see in these connecting wires, which is because of the flow of charge, that is your conduction current. And I'm referring that conduction current as IC. And the second type of current, which is actually the reason of magnetic field for loop C2 in between the two plates of parallel plate capacitor, where there is no actual flow of charge, you have this ID. So this is the correct or the modified form of AMPHER'S law. And basically this modification is because of the presence of this current here, this ID here. Why I'm saying current? Let me explain that. Since you have a magnetic field here for loop C2, and that magnetic field is due to time varying electric field. And whenever we have a magnetic field, then we can say there is current. But the cause of that current is not like ordinary conduction current. That is not because of flow of charge. That current is because of time varying electric field. Why I'm correlating this time varying electric field with current? Because you have a magnetic field, and whenever we have magnetic field, we can say there is current. But the reason of both the currents is totally different. Reason of current in loops for these connecting wires is flow of charge, whereas the reason of current here is time varying electric field. So this closed line integral of magnetic field is mu naught times the total current enclosed, which is actually the combination of IC and ID. So what is the meaning of this entire modified Ampere's law? Meaning is, significance of this law is, two factors are there which can give us magnetic field. The first one is IC, and you know what is IC? IC is the flow of charge. So magnetic field in a circuit is because of two factors. One is moving charges and the second one is ID, or you can say displacement current, and that displacement current is because of time varying electric field. So I hope up to now this is clear that in a circuit where you have this parallel plate capacitor, in the connecting wires we have conduction current, whereas in between the two plates of parallel plate capacitor again we have a magnetic field, but that magnetic field is because of time varying electric field, and that magnetic field is related to current, and that current is known as displacement current. So that is a basic idea, and this is the modified form of Ampere's law. Okay, so I hope all these points are clear to you. This is connecting wire where you have actual flow of charge and conduction current, and here you have time varying electric field which is giving us a magnetic field. So you have displacement current here and conduction current in the connecting wires, and this is your modified Ampere's law. And this displacement current, actually the value of this displacement current is epsilon naught d phi e by dt, where this phi e is actually representing the electric flux. And you know, electric flux is actually the product of electric field and area. So this term rate of change of electric flux is actually representing the time varying electric field. So this time varying electric field is responsible for ID. So this is the correct form or the complete form of this Ampere's law. B dot dl is mu naught times IC, which is your conduction current, and the second one is displacement current, which is because of time varying electric field, right? So this is your Ampere's law. Now this I have mentioned in the first slide that we are going to cover one more term which is related to displacement current, which is and that term is displacement current density. As you all know, for ordinary current or conduction current per unit area, this is known as current density. So for conduction current, we have conduction current density, which is mentioned as JC. Similarly, if you want to find displacement current density, then displacement current density, that will be displacement current upon area. For conduction current density is conduction current upon area. For displacement current, it will be ID upon A. Now, in order to find the value of displacement current density, what you have that ID. Let me derive this ID here. Give me a second. You have ID as epsilon naught d phi e by dt. This is your displacement current. And you know, in this displacement current, this phi e is electric field into area. Now, area cannot change with time. So, I can write it as A epsilon naught into del E by del T. So, this is your area. This is ID. I can write it as ID by A. So, this ID by A, from here, it is epsilon naught del E by del T. And you know, current upon area, this represents current density. And since this current is displacement current, you can write it as JD. So, this JD is epsilon naught del E by del T. Or you can say this is del by del T of epsilon naught into E. And this epsilon naught into E, this particular term, this vector epsilon naught into E is known as displacement vector. So, you can write this JD as del D by del T. So, this JD is your displacement current density, and that displacement current density is del D by del T. So this is displacement current density, and you have also seen that what is your modified Ampere's law. So this is the derivation for displacement current density, which is I del D by del T. And one more interesting point is there. The current in the connecting wires, which is because of flow of charge, that conduction current is exactly equal to the current for loop C2 in between the two plates of parallel plate capacitor. Means IC, which is there in connecting wires, that is exactly equal to ID. And you can prove it simply with the help of this one. E is equal to Q by epsilon naught for a parallel plate capacitor. If you will differentiate it, you will get del E by del T. 1 upon A epsilon naught is constant. You will get here del Q upon del T, means flow of charge. And you know, flow of charge is represented as IC. So from here, IC is A epsilon naught del E by del T. Now this epsilon naught, if you will multiply A with E, that will represent flux. So this is epsilon naught del phi E by del T. And you know, what is this term epsilon naught del phi E by del T? It is displacement current. So what you have seen here, you have seen that IC is exactly equal to ID. So in today's topic, what you have learned, you have seen that in case of electromagnetics, 4 Maxwell equations are there, and those 4 Maxwell equations are coming from 4 laws, basic laws of electrostatics and magnetostatics. And in those 4 Maxwell equations, the last equation, which is actually a bridge between electric field and magnetic field, that is your modified Ampere's law. And the modification in that Ampere's law is because of the concept of displacement current. And displacement current is just like conduction current, it is giving us magnetic field, but the cause of displacement current is time varying electric field. And the current in connecting wires, which is conduction current, is exactly equal to the current because of time varying electric field. So these are some reference books which you can use for this topic of displacement current as well as for electromagnetic field theory. That's all for today. Thank you so much.